thousand.
Yeah.
You're so shocked. You yeah. All right. DIFC. What? Okay. Phys. Ignore. Oh, come on. There we go. Alright, physics, fields, Coulombs law?
Yeah.
Yeah? Great. Did we finish Newton's law last time?
Yeah.
Yeah, so we have Coulomb and Newton to look at. Yeah, okay. Right. Oh yeah, so I probably need to open up the calculator. 2 electrons are 0.09 nanometers from 4 protons. The electrons will be drawn together by a force. Find the force. Alright, so that's Coulomb's law, nothing special there. So it's K, or 1 over 4 pi epsilon 0, times Q1. What's Q1 here? 2 electrons, yeah, and Q2?
4 protons.
4 protons, and the distance is 0.09 times 10 to the minus 9 squared. So you just put all that in the formula and you get your answer. My calculator hasn't loaded yet. Could I borrow this one? Yeah. Okay. 1 over 4 pi epsilon 0, which is 32, times Q1, which is 2e, and then 4, and then the distance squared, which is 0.09 times 10 to the power of minus 9.
Actually, you have to separate that.
Separate what?
Separate that part. Two parts.
Huh?
I mean just separate the 10 to something part, another part.
What answer did you get?
You got?
Yeah.
Nothing.
No, what answer did you get?
This.
What?
This.
The heck?
Something wrong.
Oh yeah, something's wrong.
Yeah.
Oh, I'm tired. What did I type in wrong? 1.
You know what is 2 times e? Scared 6. You have to scared 6. Not scared 6, like e to the power of 10, e to the power of 6.
Why is it e to the power of 6?
It's too early.
do you know? You know this is wrong.
6. 2 electrons for
Yeah.
proton.
Yeah. So shouldn't 2 electrons just be e plus e? 2e?
2 times e?
Yeah.
No, e times e.
Yeah.
Why would 2 electrons be e times e?
Oh. You know, you're right. Why I do that? Yeah, you're right.
Yeah.
Yeah, you're right.
I can't believe it either. I'm shocked too, because I remember last time we were talking about this, and nobody said, teacher, that's not quite right.
You're right.
I know it.
Why I do it like that? Yeah.
Come on, Bruce. I was telling my September students you will automatically lose 10% in your exam because you will do stupid things. Stupid things you won't realise it's stupid until later. So last week, for example, one of my students said there were 12 hours in a day. An example of that. I think this is an example of that.
Yeah.
So it should have been 2e times 4, whoops, flip, 4e, and then 0.09 times 10 to the power of minus 9. This is it? Alright, that's what it should be. Ah, that's so funny. Isn't that funny?
I don't know what happened last.
I don't know. I don't know. Do you know what it was? All the fasting we're doing. This is what the cause is. Because it was an afternoon class. I told you, quarter fast. Not anything between breakfast and lunch.
Not even fast.
Fifth then. Alright, we have this? Yep. Okay, second one now. An electron is orbiting 2 protons. What is the velocity? By the way, what is 2 protons from your chemistry class?
2 protons?
Yeah. What?
Helium.
Helium,
Yeah.
isn't it? Helium, yeah?
Yeah.
And 3 is lithium?
Lithium.
Yeah. So, what we've got here... Come on. Go away. Right. Proton. I think I said 10 to the minus 10.
Yeah.
And then you have a little electron here. And that's going around in a circle, and we want the velocity here. So, let's see, what could we say? I can say F equals ma, which equals mv squared over r. So, B equals F r over m square root. But we actually have a formula for F thanks to Mr. Coulomb, who said it's 1 over 4 pi epsilon 0 Q1 Q2 r squared times r. So of course that's kind of nice because it means they cancel and we can just plop in the numbers. So plopping in the numbers. 1 over 4 pi epsilon 0. Now what's Q1 here? It's an electron, isn't it? Alright, there. And then Q2 is 2 protons. And that's over 10 to the power of minus 10, and that's over the mass of an electron, which is number 3 here. I think I have all of that. Looks okay. Did we get this? Yeah. Let's put this in kilometers per second. 2,251 kilometers per second. Pretty fast. Pretty fast. Yeah. You need to write this down? Got this? Yep. The next one. So, an electron is trapped in orbit of a proton. So what atom is that? 1 electron around 1 proton. What is it? Hydrogen, yeah. Hydrogen. Yeah. No neutrons in this one. How much energy is needed to free the electrons? You may assume that the kinetic energy remains the same after being freed. So, you know, you have the potential and the kinetic at the start equals potential and the kinetic at the end, but the kinetics, we say, don't change. So what has happened is it has a negative potential, and you've given it energy to make that negative potential 0. So the question is just what's the potential energy? And we have a formula for that. It's going to be a minus number. 1 of minus 1 over 4 pi. I'll get it. 4 pi epsilon. Epsilon 0 Q1 Q2 or, not or squared. Yeah. Now, since that's very small, it'd be suitable to use electron volts. In fact, did I even say to use electron volts? Yeah. Minus. So you need 14.4 electron volts of energy to free it. 14.4 electron volts. Is that okay? Yeah? Yeah? Okay. So the last one here, a proton is fired towards 3 protons, and as the proton approaches, it feels a repulsive force. What's the value of V if the closest the proton gets to the protons is 1 nanometer? So, I'm sorry if that was a little bit unclear. What I pictured in my head was, I have 3 protons sitting here, and 1 proton here, and it's fired at a speed of V to these 3 protons, which I imagine are fixed. Although, I know in real life they'll be pushed backwards a little bit, but we'll roughly say they're fixed. So what happens here is this will come in, but it will slow down and then fire or be pushed away. So I want to know what is the V here if this distance is 10 to the minus 10 meters. So how fast was it going? Yeah, it is an energy one. So this one here has kinetic and potential, and when it reaches here it has kinetic and potential. And let's look in more detail what it is. So the kinetic will be obvious. It'll be a half v squared. And the potential is not so obvious. What would the potential be? Yeah, why?
This is not trapped.
It's not trapped, it's free.
Yeah, it's free.
It's quite far away, we imagine. So its potential is roughly 0 because it's free. Okay. Now, when it gets here, what about kinetic?
0.
That'll be 0. And its potential definitely is not 0. But its potential is also not negative.
Yeah.
Why not?
It's
It's not trapped, yeah. It's actually positive here because there's a force about to push it away, do some work. So it's the same formula except just with a positive. So these two must be equal. So you get, therefore, a half mv squared equals k q1 q2 over r. And I'm looking for the v. So we can finish up by saying v is 2k q1 q2 over mr square root. And that will give us the v. So let's see what we get here. Okay, 2 times 1 over 4 pi epsilon 0 q1. Now, to be careful here, I need to put in a 3 in one of these. And this is mass of the proton, which is number 1. And the radius is 10 to the power of minus 10. I think I said, wasn't it? Yeah. So,
no, not
no, what was the radius?
just not 10 to the minus 9.
Oh, 10 to the minus 9.
Yeah.
Are you sure?
Of course.
10 to the minus 9?
Yeah.
Oh, a nanometer. Okay. 28.8 kilometers per second.
How did you know this free or not free?
When?
Starting the initial.
Well, it's so far away from the 3 protons, there's nothing influencing it. You know, there's nothing pushing it, there's nothing pulling it, there's nothing trapping it. It's just free. And then all I've done is given it a speed. And then as it approaches the 3 protons, it gets a positive potential energy because the 3 protons are pushing it away. A bit like how this here has potential energy because gravity is, you know, pulling it down. Is this last one okay? Yeah. Sorry. Yeah. Continue. Next one. Okay, so